Have you ever just looked up at the night sky and wondered, what's the story up there? Well, the universe actually has one. It has an origin story, a kind of recipe for how everything we see was made. Today, we're going to be cosmic detectives, and we're going to learn how to read that story. And you know what our biggest clue is? The oldest message in existence: starlight. So right off the bat, you might be thinking, how on earth is this even possible? I mean, we can't just fly out to a star that's millions of light years away and scoop up a sample, right? Well, the secret is, we don't have to. The answer travels all the way across the universe to us. We just have to know how to read the message when it gets here. You see, the real secret is hidden inside the light itself. Star night isn't just some plain old white glow. Nope. It's a message packed with information. You can think of it like a cosmic fingerprint, carrying all these little details about the star it came from, and even the stuff it passed through on its way to us. Our whole job is just to decode that message. And our number one decoding tool is something called a spectrum. Now, you've definitely seen this before. It's what happens when a prism, or even a raindrop, splits sunlight into a beautiful rainbow. By doing the exact same thing to starlight, we can uncover all these clues that are totally invisible to the naked eye. Okay, and what's really crucial here is that not all spectra look the same. Light from the super hot, dense core of a star gives you that perfect, continuous rainbow. But, and this is the key part, as that light travels through the star's cooler outer layers, certain very specific colors get absorbed by the gases there. That leaves behind these little black lines in the rainbow. Those lines, whether they're dark absorption lines or bright emission lines from a glowing gas cloud, those are the clues we're hunting for. And here is the absolute knockout punch. Every single element on the periodic table, we're talking hydrogen, helium, carbon, everything, it absorbs and emits light at its own unique set of frequencies. This creates a pattern of lines that is as distinct as a fingerprint or a barcode. So if we look at a star spectrum and we see the barcode for helium, well, we know for a fact there's helium in that star. It's literally that direct. So what happened when astronomers started using this amazing technique? When they started collecting and analyzing all these cosmic fingerprints from all across the sky, they didn't find some super complicated mix of 100 different elements. What they found was a recipe for the entire universe that was, well, it was shockingly simple.
And this is it. This is what they found. The recipe for pretty much everything we can see is incredibly basic. About 74% of it is hydrogen, the simplest element there is. Another 24% is helium, the second simplest. And everything else, everything else, every element that makes up you, me, the Earth, all of it, is crammed into that tiny little 2% slice.
But within those numbers is the most important clue of all. When you measure it all by mass, the ratio of hydrogen to helium is unbelievably consistent. It doesn't matter where you look in the cosmos, it's always about 3 parts hydrogen for every 1 part helium, a constant 3-to-1 ratio. So now we have our central mystery. Why? Why this specific recipe? It's clearly not random. This stubborn, consistent 3-to-1 ratio is a giant, flashing clue pointing to some kind of single shared origin for all the matter in the universe. But what in the world could have cooked up this exact mixture? Well, to figure that out, we have to rewind the clock, way back. The answer, it turns out, is hidden in the very first moments of the universe itself. The Big Bang Theory isn't just some vague idea that the universe is expanding. It gives us a really precise timeline for how matter itself was built, step by step, as the universe cooled down from this unbelievably hot, dense state. Right at the very, very beginning, it was just way too hot for anything we'd recognize to exist. There were just the most fundamental particles, things like quarks and electrons, whizzing around. But as the universe expanded and started to cool off, quarks were able to clump together to form protons and neutrons. Then, a little later, those could fuse together to make the first atomic nuclei. It was actually much, much later before it was cool enough for electrons to finally get captured and form the first complete stable atoms. But the critical moment for our mystery happens at just 3 minutes after the Big Bang. At this point, the universe was finally cool enough for protons and neutrons to stick together and form helium nuclei. And the physics of that moment, the temperatures and densities, it all locked in a very specific result. For every 1 helium nucleus that was made, about 12 hydrogen nuclei were left over. And that is what created our precise 3-to-1 mass ratio, right there at the dawn of time. Now, for the next 380,000 years or so, the universe was basically a thick, hot fog. It was this cosmic soup of nuclei and free electrons, and those electrons were constantly batting light particles around, so light couldn't get very far. But then, once the temperature dropped to about 3,000 Kelvin, those free electrons were finally captured by the nuclei, forming the first real atoms. And just like that, poof, the fog cleared. With no more free electrons to block the way, the universe became transparent, and all that trapped light was finally set free to travel across the cosmos. Okay, so let's recap our detective story. We analyzed the starlight and found a really weird clue, that universal 3-to-1 ratio. Then we rewound the clock with the Big Bang theory and found a physical process that perfectly explains how that ratio was created. Now it's time for the final piece of the puzzle, the ultimate proof that closes the case. And here it is. This is the beautiful part. The Big Bang Theory isn't just a story, it's a mathematical model. It makes hard, testable predictions. And one of its core predictions is that the primordial gas cooked up in those first few minutes should have a hydrogen to helium mass ratio of, you guessed it, about 3-to-1. And when we point our telescopes at the oldest, most pristine stars and galaxies out there, when we read their cosmic fingerprints, what do we find? Exactly the same 3-to-1 ratio. The prediction from the theory and the observation from the sky match perfectly. This is no coincidence. I mean, this is absolutely stunning. The fact that a theory about what happened in the first 3 minutes of time perfectly matches our observations of stars that are billions of years old, that is one of the most powerful pillars of evidence we have for the entire Big Bang model. We read the clue in the starlight, and it pointed us right back to the beginning of everything. So, case closed on the universe's original recipe. But this just raises one more giant question, doesn't it? If the Big Bang only cooked up hydrogen and helium, what about that other 2%? Where did all the good stuff come from? Like the carbon in our bodies and the oxygen we're breathing right now? Well, that, as it turns out, is a whole other story. One that was forged in the fiery hearts of the very stars we just used to solve our first mystery.